Okay, so today we're doing bonding. The syllabus outcomes, there seems to be a lot here, but uh, it's not too bad. Firstly, we're going to investigate the role of electronegativity in determining the ionic or covalent nature of bonds between atoms. And we're going to investigate the differences between ionic and covalent compounds through using nomenclature, valency, and chemical formulae, examining the spectrum of bonds between atoms with varying degrees of polarity with respect to their constituent elements' positions on the periodic table. Now there's a few grayed out bits that we're actually going to do in future lessons. So that's the Lewis dot diagrams, the Lewis structures, as well as modeling the shapes of molecular substances. So there's some revision questions at the top of page 84. So please go through them. So the answers to those are: we measure atomic radius by first measuring the distance between two atoms of the same type. First ionization energy is the energy it takes to remove an electron from an atom, and an electronegativity is an atom's ability to attract electrons. So what we're doing today is bonding. So we've previously talked about ionic compounds and covalent compounds, but what exactly are they? Well, let's have a look. So in compounds, there's several different types of bonds. So when atoms are joined chemically, they're referred to as being bonded. And there are two main types of bonds that we encounter in chemistry: ionic bonds and covalent bonds. So these are the main ones. There are other types. The other main big one is coordinate covalent bonds, hybridized bonds. There's all sorts of things. These are the two that we're going to look at today, and the important ones. So ionic bonds occur when there is a complete transfer of an electron from one element to another. Okay, so the element that has a lower affinity for electrons will lose an electron, and the atom with the greater affinity will gain the electron. Now, the example that we've got, sodium and chlorine. If you stick sodium metal into chlorine gas, it's a very energetic reaction. Includes lots of flames and sputtering and all sorts of things. And that's because sodium really wants to get rid of its electron. Chlorine really wants to take it from it. And so that's where we get this ionic bond. Now, um, once that happens, we get two ions. So we get the sodium plus ion, the chlorine minus ion, so also called the chloride ion. And then what happens after that? We get electrostatic effects hold the atoms together. So I think I mentioned it in a previous lesson that if you have a positive charge and you have a negative charge, there's a force between them. Anyone that's doing physics will hit that in module 4, but there is a force felt between two charges. And the forces between these atoms are very strong and produces compounds with no freely moving electrons. And so this allows us to explain some of the properties of the ionic compounds. Most ionic compounds have a high melting point, okay? Just because those atoms are very strongly bound to each other, so they don't actually like to start flowing into a liquid. They're also usually soluble in water. Again, that's a electrostatic effect. They also conduct electricity when dissolved in water. Okay. Um, Basically, pure water is a very terrible conductor. You need ions in there, and that's because electricity is the flow of charge, and we need something to allow that charge to flow through water. And it usually it comes from ions. Now, the next are covalent bonds. So covalent bonds occur when two orbitals of two atoms overlap and they share electrons. Okay, so this is where the name covalent comes from. So we're looking at the valence shell and they overlap and kind of share electrons. The electrons will spend some time around one of the atoms and the rest of the time they spend it around the other atom. So they're kind of going around one, so let's say we had two atoms like this. They'd spend some time over here, then go over here and go back and stuff like that. Okay. Now, because of this sharing, atoms in a covalent bond fulfill their octet rule. So here's an example. So here we have atom 1, which is a non-metal. Atom 2 is also a non-metal, and they form this covalent bond. So we basically get these two electrons forming a bond there where they share their valence electrons. And so if we look at this covalent molecule, atom A has 8 electrons in its outer shell. Atom B also has 8 electrons in its outer shell. And so this is where we fulfill the octet rule, even though we're not transferring. Okay, so it still allows that. Now, the amount of time that an electron spends around an atom depends upon its electronegativity. The more electronegative an atom is, the more the electrons will spend around it. So for example, if we had something like chlorine bonded to a carbon, chlorine's much more electronegative. So we'd get the electrons staying around here, going back for a bit, but then spending more time around the chlorine than the carbon. Okay. This gives rise to what we call polarity. So it's a physical property relating to induced electric fields. It basically gives us this semi-permanent electric field within the molecule. Okay. As the difference in electronegativity increases, the polarity of the bond increases. If the difference in electronegativity is too high, though, the bond stops being covalent and we just get an ionic transfer. So rather than having this sharing, if that difference in electronegativity is too high, it just rips it off and that's the end of it. And so this is how we figure it out. So if we find the electronegativity of both of the atoms, so we have a look at that table from last lesson. If we find that the difference in electronegativity is less than 0.4, it's what we call a nonpolar covalent bond. And so the electrons generally share, sorry, the atoms generally share the electrons quite evenly. Now, if we have between 0.4 and 1.5, we start having polar covalence. So this is where we start getting those semi-permanent, so those permanent electric fields. Between 1.5 and 2, if the molecule does not contain a metal, so if it's non-metals only, it still stays as polar covalent. But if we introduce a metal, it suddenly becomes an ionic compound. Okay. But if the electronegativity difference is greater than 2, then it's ionic regardless. Okay. So what we can do is we can use that table and the electronegativity table in the previous lesson. It was on page 79, just at the bottom. We can use that to determine the type of bond present. Okay. So before we do some examples, we'll just show you how to write polarity. So sometimes you'll actually be required to denote the polarity on a molecule. So here we have an oxygen and a hydrogen bonded to each other. How do we write the polarity? Well, there's two ways. The first way is with this little arrow with a cross at one end. So we put a little plus on the side that has the lower electronegativity, and we draw the arrow towards the atom with the higher electronegativity. The other way is writing these little symbols. So this is delta plus and delta minus. These are what we call partial positive and negative charges. So normally you're used to formal charges at this point. So it's a +1, it's a +2, +3, or -1, -2, -3. These ones are where we have a uneven distribution of electrons that create some of those electric fields. So it's not enough to be a full charge, like it's not enough to be an integer charge. It'd be less than that. So it's only partial positive or partial negative. Okay, but it still allows electrostatic interactions. So determining the type of bond present. So determine the type of bond present between carbon and fluorine. So what we have to do is we have to use that table on page 85, as well as the electronegativity table on page 79. So we first figure out the electronegativities of each of the atoms. So carbon has electronegativity of 2.5, fluorine has an electronegativity of 4. What's the difference? Well, it's 1.5. And if we have a look at the table, 1.5 lies in that third row. So it's ionic if the bond contains a metal, polar covalent if the bond contains only nonmetals. We have carbon and fluorine. Both of them are non-metals. So this one ends up being polar covalent. Now, the next one, determine the type of bond present between silicon and nitrogen. So again, we go to the table of electronegativities, we find that silicon has an electronegativity of 1.8, nitrogen has an electronegativity of 3. The difference being 1.3 puts it immediately, 1.2 puts it immediately in polar covalent territory. Okay, now this one, again, it's 1.2, so it's less than 1.5, so it's just immediately polar covalent. So, use the electronegativity table on page, what did I say, 79 to determine the type of bond between those. So pause this, have a go, and come back for the answers. So carbon and chlorine, we'll find that that one's a polar covalent. Sodium and chloride, that's an ionic. Aluminium and chloride, again, ionic, basically because that aluminium is a metal. Carbon and oxygen is polar covalent. Nitrogen and iodine is polar covalent. Phosphorus and sulfur is a non-polar covalent. Okay, so hopefully you got those. If you're not sure, come and see me, and we'll move on to the next bit. So the next part of bonding, we actually no, that's it. Sorry, I thought we had more. So that's it for bonding at this stage. So let's have a look at a bit of a summary. Ionic bonds involve the transfer of electrons. Covalent bonds involve the sharing of electrons. Nonpolar covalent bonds have the electrons around both atoms approximately equally, and polar covalent bonds have the electrons shared unequally and therefore produce an electric field. Okay, so get that summary down, and that is all for today.